All right, lecture 50, type 1 and type 2 errors. Very important concept in hypothesis testing. First off, let me say, in this context, the word error, if you read here, does not mean that we did something wrong. That's not the kind of error we're talking about. Error has a very specific meaning here. It means that in your hypothesis test, you've done it correctly, and still you're led to the wrong conclusion. We know that can happen, right? We know it can happen that you can get an unusual result, a t-score that's way out there, causing you to reject the null when in fact the null is actually true, right? You can just get an unusual value. And just by chance. When this happens, you've done nothing wrong, but your conclusion is still incorrect. This is an example of a type 1 error. So a type 1 error occurs when we reject a null hypothesis that is actually true. Graphically, what does that look like? Actually, I guess I don't need to have a vertical line here. I'm going to reject a null hypothesis that's true. So the null hypothesis would say that, my mean is mu sub 0. So heck, it actually is mu sub 0, right? It actually is mu sub 0. And this, of course, this extends out this way and this extends out that way. What I say, the mu naught is correct. It is the actual value of the mean, but it just so happened that, so here's maybe our cutoff value, our CV. Okay, so then this area equals alpha, so we're back to thinking of having a significance level again. And it just so happens that X bar is out in the rejection region. X bar just happens to be unusual. Okay, so the null hypothesis is correct. There was no change or whatever. And we have the mean that the null hypothesis says there is. But then we take our sample mean from our sample, and it just happens to be an unusual value for the sample mean, and that slides us way out there past the critical value. So here we are rejecting H naught. But H naught is actually still true. This is a type 1 error. So one more time, an error doesn't mean we did something wrong. Error here means our particular sample, assuming we gathered it correctly, just happened to be an unusual sample that gave us an unusual value for the sample mean, leading us to believe that our null hypothesis is false, and so we reject it, but maybe the null hypothesis really was true, and we're saying that it is, in this case, true. All right, what is the probability of a type 1 error? Probability of type 1 error is actually pretty easy to see. If the null hypothesis is true, we always draw the curve assuming the null hypothesis is true, right? And then if we get an unusual value, that makes us think the null hypothesis was false and we should have actually shifted, right? So standing right here is the cutoff value, the critical value beyond which I'm going to declare this to be unusual, assuming the null hypothesis is true. And that area of that tail is alpha. So the probability that this curve is exactly correct, and I just happen to get an X bar that lies out here, is the probability of this whole tail. It's the tail probability associated with the critical value. It is the significance level alpha. Right? So the probability of a type 1 error is just the significance level, okay? And that's why we start with some significance level as a cutoff probability. It's really a cutoff probability for a measure of unusualness, and it's also giving us the probability that we actually will, in the case where the null hypothesis is true, we actually make an incorrect conclusion. A type 2 error, then, that's type 1. Type 2, I say here, okay, so let me read the paragraph there. There's another way an error can occur, of course, if our test statistic is not extreme, so that it has a fairly large p-value, we would typically fail to reject the null, all right? But of course, the null hypothesis could still be false. The mean or other parameter could actually be different from what the null says it is, but we would not be able to detect that given the value of our test statistic. This is what is meant by a type 2 error. So let me write that down. Well, I read one right here. It says a type 2 error occurs when we fail to reject the null when it is actually false. So here's the picture. So we come along here, and here's mu naught, all right? And maybe our, let's see, our critical value's out here, right? Okay, but maybe our test statistic, let me change colors here a little bit. Maybe our test statistic does not lie, I'm going to say X bar, doesn't lie in rejection region. Okay, but it turns out that in fact, so we would fail to reject. Here we fail to reject. But maybe H naught is false. In other words, maybe this is wrong and the true mean really is over here, right? The true mean really is over here. So we have, you know, our curve comes more like that or something, right? So it really is the case that the mean is actually, in this case, bigger than what the null hypothesis says. But it just so happened that the value of X bar we got, again, was tucked in close enough to mu naught that it didn't fall in the rejection region, so we failed to reject it when in fact we should have, because the mean is actually different than that, right? The alternative hypothesis is true. Okay, again, it's not an error in anything we did. It's just the particular sample we got just wasn't unusual enough for us to catch sight of, or I guess actually the way I drew this, the shift would actually be to the left, wouldn't it? It doesn't matter. But yeah, if I think it's, no, it'd be this way, right? But it wasn't extreme enough for us to make that conclusion, right? It wasn't extreme enough for us to make that conclusion. So it's just the particular sample we got gave us that. All right, so I say here then, I'm not going to write it again, but a type 2 error occurs when we fail to reject a null hypothesis, as in this case when in fact it is actually false. There was a difference in the mean. That mean had changed. The probability of committing a type 2 error whose symbol is, well, alpha is the probability of type 1, not surprisingly, beta is the symbol for type 2. It's generally complicated to compute. You have to make some assumptions to get there, and we're not going to worry about it right here, at least not for now. I may revisit it later, but I don't think we need it for anything we're going to do anytime soon. Okay, I say here the following table summarizes the type 1 and type 2 error situations. Okay, so look what that table says. It says that up top, it says the reality of the situation. You know, H naught is true or H naught is false. And off to the left, it says what our test is telling us to do, to reject H naught or fail to reject. So we have over here, let me see, I guess I have, I guess I'll do it like, maybe make it a little bit bigger. All right, so I have this and I have that, and then in here I have, all right, and this is, what do I have? I have null is true, H naught true, H naught genuinely false. It's actually not right. And over here, we reject H naught, and here we fail to reject H naught. And what's going on? All right, let's look at this one first. H naught is actually false, and we reject H naught. This is good. Test leads us to do the right thing. Right? Let's go down to this one. H naught is true, and we fail to reject H naught. Ditto. Good. Test leads us correctly to do the right thing. What about this square? H naught is true, but we reject H naught. That's a type 1 error. If H naught is false, but we fail to reject it, that's a type 2 error. All right. And so look what I say down below there. This is a good table to have memorized, okay? What I say below is, what I say, of course, and I don't say anymore, so you need to write some things in. If we reject H naught, and where is it that we're rejecting H naught? We're rejecting it along this row right here, correct? Well, the thing we'd like to know is which column are we in? When we're rejecting H naught, the test statistic is way the heck out there, whichever way. Are we making a type 1 error, or did we make the right conclusion? If we reject H naught, did we make a type 1 error? Well, what if we fail to reject? If our test statistic is not, if we fail to reject because our test statistic is not so extreme, okay, I should always say reject H naught, then what could happen? Well, look, we're down here, we failed to reject. Is this a good thing? Did our test lead us to do the right thing? Or did we make a type 2 error? Did we make a type 2 error? The answer is, in either case, we don't know, right? We don't know what we did because all we have is what the test told us. Over here it says what the test told us. Here's the reality. We don't know reality, right? This is God knows this. God knows whether H naught is true or H naught is false. All we can do is do a statistical test and decide whether we should reject H naught or fail to reject H naught. So once we do that, we're locked into one row, but we don't know which column we're in. We could be doing it right, or we could be making either a type 1 error or a type 2 error. So, you know, what do you do? Well, the answer is that you can't know for sure, but what we'd like to do is reduce as much as possible the probability that we make an error, right? I would like to make it so that let's just say, for example, I'm very unlikely to make a type 1 error, okay? How do I do that? How do I make it real unlikely? Well, I want to decrease the probability, and remember the probability was the significance. So I can decrease the probability of making a type 1 error by making the significance really low, right? And in fact, I think I say this down here. Yeah, so type 1 and type 2 errors, I go ahead and say here, they play off of each other. To decrease the likelihood of one, we automatically find the likelihood of the other is increased. And that's really what I'm getting at here. And I mentioned there without increasing the sample size. I'll say more about that later. But why is it that they play off of each other? And what I say here is we decrease the probability of type 1 error by making it, use this language, making it harder for, how do I say it? Making it harder for the test statistic to lie in the rejection region. Right? If I make it difficult for the test statistic to make it all the way over to the rejection region, then I'm not so likely to reject H naught. I'm not so likely to get a type 1 error. And so in other words, so we slide the critical value out, slide CV out. In other words, make the critical value more extreme. But if I make that critical value more extreme, I have shrunk alpha. So let me say, so shrinking alpha. Okay, so that makes sense, doesn't it? If I slide that way the heck out, I make it harder for the test statistic lot to lie in there. So in the event that I just happen to get kind of an unusual value, H naught is true, but I get kind of an unusual value for my test statistic, if my critical value is way the heck out there, you know, it'd have to be a very unusual value to get out that far, and that's just less and less likely. Right? So we can decrease the probability of type 1 error by doing that. So what does that do? This makes it more likely that, so keep this in mind, I have put my critical value way out there. It makes it more likely then that even if a test statistic is unusual enough that maybe we should have rejected H naught, it might not get out there far enough, right? So we might fail to reject H naught when we might fail to reject H naught when in fact H naught is true. So let me say, so it makes more likely that we will fail to reject H naught when H naught is true. If we have slid the test statistic, when H naught is false, that's my problem. Forgive me, I meant when it's false, right? We are more likely to reject, that we will fail to reject H naught when H naught is false. This is a little bit complicated, right? So forgive me, I just messed it up a little bit there. Okay, because why? Because think about this. The critical value is way the heck out there. Well, suppose H naught is false and the mean really is up here more. Well, even though it's up here more, if that critical value is way out there and I get an extreme value for my X bar, it might not be extreme enough. So I will fail to reject the null, even though the whole curve really did shift and the null really is false. All right, so if we slide the CV in, what we could do is we can make the critical value less extreme. Then what happens? It's a lot easier for your test statistic to lie beyond the critical value. So it's a lot easier for us to reject H naught. We were less likely to fail to reject H naught because it's easy to get into the rejection region. It's easier. So we're less likely to fail. So the probability of type 2 error goes down, but then it becomes so much easier to reject H naught because our critical value is in that we increase the probability of type 1 error. So let me just see how I want to conclude this. So we can slide the CV in, then probability of type 2 goes down, then probability of type 2 error decreases, but the probability of type 1 error goes up. So it depends on where we set that significance level, where we slide that critical value to. If we slide it way the heck out, we're very unlikely to make a type 1 error, but we're more likely then to make a type 2 error because it's just more likely that we will fail to reject because it's just too far out to reach that critical value. If we slide it way in, it's much easier to reach the critical value. We're more likely to reject, which means we're more likely to make a type 1 error. We'll be less likely to make a type 2, but more likely to make a type 1. Okay, so how do you play them off of each other? All right, how do you play them off of each other? You know, what you'd like is to decrease the probability of both type 1 and type 2 errors. Let me just say offhand that you can do that if you get a larger sample size. I'm not going to go into detail right now, but if you're able to collect a larger sample size, you can get statistical significance when you might not otherwise get it. All things kind of get better, and in particular, you can decrease both the probability of type 1 and type 2 errors. But given a particular sample size in a particular situation, how do you decide how to play these off of each other? How do you decide where to put your critical value to balance the probability of type 1 errors with the probability of type 2 errors? And the answer is it really depends on the situation. It depends on the importance of making one kind of error versus another kind of error. And I guess I have a picture here. So I say clearly we should set alpha with all of this in mind. And I guess if I draw the picture, this is what I was saying earlier. So suppose we just have this, okay, and let me say we go way out here and we have small alpha. If you have small alpha, the probability of type 1 error is small. Probability of type 2 error is larger. Let's just say not so small. If instead, so here's my CV way out here. If instead, let me kind of exaggerate, let me put the CV way in here, all right? So now alpha, not so small alpha. In this case, probability of type 1 error is not so small. Probability of type 2 error is now smaller, okay? I'm not so likely to fail to reject a true null, that's type 2, because it's easy to end up over here in the rejection region, right? I'm not so likely to fail to reject, end up just like right in here, okay? So that's why probability type 2 is small there. All right, and I say if type 1 and type 2 errors play off each other, to increase the likelihood of one, oh no, sorry, I already read that. I got one more thing I want to say here, though, at the bottom. One more thing I want to say, and that is, so how do we decide on that significance? How do we decide our alpha value? And like I say, it depends on the consequences of making a type 1 error versus making a type 2 error. For example, suppose that we're looking at the mean levels of a dangerous pathogen. We probably want to set the significance to be a high value. All right, and why is that? Significance. In other words, the probability of making a type 1 error to be kind of high. Here's why. So let's suppose if a safe mean level of some dangerous pathogen is mu sub 0, then we're going to test the water for E. coli or something like that. All right, the null hypothesis would be that mu is mu 0. The alternative hypothesis would be that mu is greater than mu 0 because we want to catch it, right? I want to catch, it's bigger than this safe level. We got to keep people out of the water, right? Well, so if you think about what you want to do here, I want to have it be a pretty good chance, don't I, that if the null hypothesis is false, that I catch it, right? I want it to be that if, in fact, the mean level is kind of high, I want my test to tell me that, right? So if I set my significance level to be pretty high, then my tail probability is for my critical value is big enough. My critical value be in close enough that my test level, my test statistic for the sample mean is easy to fall into the rejection region. All right, so if it is a dangerous pathogen, we want it easy for the test statistic to lie in rejection region. All right, so this means I want a big alpha. Want a larger alpha, relatively large alpha. Okay, so what is that? That's saying that the probability of type 1 error is going to be fairly big, right? The probability of type 1 error, type 1, is not so small. What is a type 1 error in this case? Type 1 error is I'm rejecting the null, so I would say that the water tests positive for E. coli. I would say I think mu is bigger than mu naught, tests positive for a dangerous level. All right, so this would be what we would call a false positive. All right. But what happens then for what's a type 2 error? If in fact we okay, so the probability of a type 1 error then is that we rejected the null when in fact the null was true. All right, so the water really was safe. Water was safe, right? H not true, but we say stay out. We reject H naught, right? All right. If in fact we had a type 2 error, what would happen with a type 2 error? For a type 2 error, we fail to reject a null hypothesis that's, have I said it wrong? Oh my gosh, have I said it wrong? A false positive is when we reject a null hypothesis that is true. Okay, no, that is correct. It's a false positive. Type 2 error, let me just say up here. Type 2 error, for a second I thought I did it wrong. Type 2 error is a false negative. Okay, here we have rejected the null hypothesis when it is in fact true. Over here, we failed to reject the null hypothesis when it is in fact false. All right, and that's when we have a bad situation, right? When we have a type 2 error, we are saying that the null, we're saying we are rejecting the null. I'm sorry, we're failing to reject the null. We are, I'm going to write this in. We are failing to reject the null. So the test is negative. We don't believe this, but the null is in fact false. So in this case, the null is false. So water is dangerous. But we say go ahead. I'm running out of space here. We say go ahead and jump in. Right, we say go ahead and jump in even though the water is dangerous. So clearly what I'd like to do is decrease probability of type 2 error. Decreasing the probability of type 1 error means that we're keeping people out of water when in fact they could have gotten in and had fun. That's not so good. But over here, the type 2 error is we're telling people to get in the water when in fact it's dangerous and they could get ill. So this is the probability we want to decrease, right? We want to decrease the probability of type 2 error. Doing so increases the probability of type 1 error. So if we set the significance level fairly high, we might get a lot of type 1 errors. We might be saying, oh, dangerous level, dangerous level, dangerous level, when in fact it isn't always that way. But we're much less likely to say, oh, no, the water's fine when it isn't, right? So you can see here's an example where type 2 error is more important to keep that small than it is to keep type 1 error small. And it can, which one you want to keep small can depend on the application, right? But this is just a little flavor of how we have these two kinds of errors and they do play off each other a little bit.